Hi, my name is Joseph, and I want to discuss scaling Postgres multiprocess architecture because it's not just about throwing more hardware at the problem. Each connection carries some hidden tags, and it could be Linux level memory and CPU overhead, or Postgres level MVCC and locking constraints. So, to manage high performance workloads, we need to understand these limits. So join me for a deep dive into these topics because we shall stop guessing and start tuning our systems. So let's start with Linux and Postgres in the multiverse of connections. I work for a German company called Credativ. We offer support for open source products. Postgres is one of our biggest topics, and we also offer complex solutions based on Kubernetes and Proxmox. My whole life was about the different types of data processing. I worked with a majority of big databases, with NoSQL solutions, with different solutions for data ingestion and ETL processes, built some data warehouses, lakehouses, and lately I do similar stuff also with AI and machine learning. If you would want to connect with me, here are some links to LinkedIn, articles which I have on Medium, recorded talks on YouTube. So don't hesitate, contact me. We can discuss these things. Let's dive into Postgres multiprocess architecture. This solution was chosen in 1990s for higher stability, and those processes are separated, isolated, very safe. But it also means that they cause some overhead on CPUs and memory usage, and they need some interprocess communication, which is done using shared memory on Linux. This diagram explains roughly how it looks like. So we have here two different processes with different process IDs, and each process has its own private code, data, heap memory, stack, and other stuff, and also isolated virtual address space. And they share kernel resources and shared memory. There are ongoing discussions about switching Postgres into thread-based architecture. But problem here is that those threads they run always in scope of some process. So here we can see that actually that heap memory will be used by all threads running inside this process, which means that developers must be really cautious to not overwrite parts of heap memory which are used by other threads. As I learned from Boris Momjin from his talk on German conference, there are plans to implement mixed architecture into Postgres to have something similar like Oracle. So we will see how it will turn up. Uh, in Linux philosophy, everything is a file. So also interprocess communication is implemented as special file system, so-called tmpfs file system. And there are three ways how to access this tmpfs. Uh, the oldest one is so-called System 5. A new so-called internal mount inside the kernel is mapped as def0 mounting point and used by mmap function. And there is also this def-shm directory, which is also really important for Postgres because here Postgres creates files for interprocess communication. We can find here files for asynchronous I/O interface, for parallel queries, and we can also, as users, interact with this tmpfs. But we must understand that this is direct access into memory. So by using it, we are actually eating the memory on the machine. When it comes to memory, this is another quite important limitation of scaling Postgres to many connections because 64 bits virtual address space must be mapped to physical addresses. Currently, not a whole 64-bit range is being used, usually 48 up to 57 bits. And that thing is implemented in very lightweight hierarchical tree of 4 or 5 tables, and they contain pointers to the next level or physical mapping. And those are these tables. So on the top we have page global directory, and those 3 tables on the bottom, they can contain physical allocation. So page upper directory contains allocations of huge pages in 1 GB size. Page middle directory allocation of those 2 MB huge pages, and that lowest level page table entry maps those standard 4 kilobyte pages. In Postgres, every process is created as a fork of main Postmaster. Fortunately, this forking process is quite lightweight. So, and even if Postmaster already uses the whole capacity of shared buffers, not all that mapping is actually copied into newly created connections, only necessary parts, and that child process fills its tables when it does not find physical mapping in the translation look-aside buffer. Shared buffers can use huge pages and actually should, as I will show on further slides. Connections use only those small standard 4 kilobyte pages. And we have also this mechanism of transparent huge pages in kernel, but it should be disabled for Postgres because it can cause quite big performance issues. And I have different talk and also workshop about these issues. So if you want, look at my slides about shared buffers. And here is explanation why that mapping in huge pages really matters. Because if we neglect it and we use standard 4 kilobyte pages for mapping shared buffers, and then for 1 GB of buffers mapped in these standard pages, we will need up to 2 MB of PTE table, which actually with 8 GB buffers and 1000 active connections can theoretically grow up to 16 GB of PTE tables. It sounds like mistake, but look at that article which is linked in that blue text. It's Percona article where they analyze these things on a big database machine, and in their case, those PTE tables reach something like 25 GB. So mapping shared buffers in huge pages is a really good idea. And here we can see the difference. If we map 1 GB buffers in 2 MB huge pages, we need just 4 kilobytes of that PMD middle directory table. So with the same example, 1000 connections and 8 GB of shared buffers, it will grow only up to 32 MB of PMD tables, which is significant difference. And here are 2 commands which we can use to examine situation on particular machine, either on the whole machine in that meminfo file or for specific process in its status. We have now a new toy called NUMA architecture. Originally, we had symmetric architecture, meaning all CPUs access the same memory using the same memory bus, which with growing number of CPU cores actually caused huge problems on that memory bus. So we now see internally machines being divided into NUMA nodes with dedicated CPU cores, which they have each own memory banks and local memory bus, and also remote access between those NUMA nodes. So it's more or less something like several physical machines connected internally with very quick bus. But this remote access is always slower than that local access inside specific NUMA node. Linux kernel offers some NUMA balancing mechanism, and it can automatically migrate memory pages and processes between those nodes. And according to benchmarks, it seems to be good enough for general workloads. Question is, what about Postgres? I had great opportunity to test Postgres 18.3 on Phytium machine, 64 cores of ARM64 architecture, divided into 8 NUMA nodes. 4 nodes with memory and 4 nodes without memory. It was very interesting configuration. Here is diagram showing this situation. Those green nodes, they have memory, and those gray nodes are without memory. Each node has 8 CPU cores. And in firmware, there is this table of NUMA distances, which shows theoretical penalties if we access resources across those nodes. So idea is that when we access resources on the same node, and that distance is marked as value 10, and with each jump between those nodes, it adds additional 10. So when we look back in this diagram, we see that worst case scenario here is communication between node 0 and node 6. And it is shown in this distance table as penalty 50, that red penalty. But these distances are theoretical. So, in scope of this problem, we must also discuss binding policies on NUMA architecture, because we can pin either memory or CPU to specific NUMA node or a list of nodes. And for Postgres, this is a hard limit, because uh, when we pin that Postmaster process, then every fork will inherit these policies. So Postgres will use only those resources which are dedicated for it through these binding policies. And therefore, if we want to pin Postgres to specific nodes, we must also make sure that resources are sufficient. I tested all pinning variants on that Phytium server, benchmark some mainstream types of workloads which I could think of. And at the end, I actually realized that those results are not statistically significant. Benchmark results were inconsistent. And from my perspective, for those types of workloads, I could test that NUMA latency was insignificant. So that distance table actually badly exaggerates. So what I found is that pinning Postgres to specific nodes is useful for workload isolation. So we can, for example, run multiple databases on one big machine and pin these different databases to different NUMA nodes, and that way isolate them. So recommendation is to use this interleaved NUMA policy either for the whole machine or those few nodes which we want to use, because in that ways those processes and their memory are distributed evenly across those dedicated nodes using a round robin policy. Context switching and Linux scheduler are another interesting problem when it comes to too many connections. Here there is some diagram, quite simplified, but it's still difficult enough, which shows how that context switching works. Generally, I think we understand it. CPU core runs first process, then that run is interrupt. The whole status of process is being saved, and then another process is being loaded, gets some runtime on CPU, again interruption, and the whole game is being done as many times as it is necessary. And here comes question of different schedules on Linux, because in these days we witness a big change in this schedule. Originally, we had this completely fair scheduler, and idea was philosophically quite nice. Let's give every process exactly the same share in exactly the same moments, which is shown on this very simple diagram. We have three different processes, and we can see that characteristic of that load is completely the same for all three processes. But those processes are different, and especially in these days when we get quite quick data in some cases, which in this case is that process one audio stream. Those are processes for which latency matters. Therefore, starting from Linux kernel 6.6, we have new so-called earliest eligible virtual deadline first scheduler. It's amazing name. I really love it. But it precisely says what it does. It gives every process uh, as much as a small latency as possible according to calculated needs of that process. So the whole idea is depicted here. Now we can see that these three different processes are processed differently. Again, in a longer scope, each of them got exactly the same runtime on CPU, but it is structured differently. So that audio stream, which is very sensitive to latency, gets processing time more often with short latency. Of course, that processing interval is shorter in this case, but it improves the whole behavior of that audio stream. On the other hand, that process 3 compiler really benefits from longer uninterrupted intervals of CPU runtime. So the whole thing should run much better. And as I said, that change comes with kernel 6.6 and newer. So we now see this change of behavior of latest distributions of Linux. From Debian 12 used the old scheduler, Debian 13 jumps to new scheduler. The same with Red Hat Linux version 10. And as I know from discussions with clients, they already see differences in behavior of Postgres when they upgraded Linux version. And suddenly, performance of Postgres was better, even without any changes in Postgres settings. So problem with that old scheduler was and that completely fair scheduler was actually sort of unfair to very short bursty workloads, very short transactions, very short selects, and that average fairness was actually hurting performance here. And that new earliest eligible deadline first scheduler actually prioritize processing of these bursty connections. So we see better latency and they are being processed earlier. And there are some discussions about machines with predominantly analytical workload because there could be some problem with more context switching, but we can actually tweak it using Linux policies. So we will see. And people often ask, okay, this is nice, but how many connections we shall have per CPU core? So we must think in scope of active connection on one CPU core, because this is what makes CPU to do real work. So when we have typical transactional workload on modern SSD storage and shared buffers in huge pages, then up to 4 active connections per one CPU core is definitely okay. If we have those very short bursts of transactions, very small transactions, then even up to 6 or 8 could be okayish, but it really depends on workload. With older hardware and without huge pages, of course, throughput goes down. For analytical workloads, we must use really one connection per one CPU core. If we have parallel workers, then we must also dedicate cores for each worker. Um, we also need to understand memory usage per connection. So this is typical situation on machines that output from top command shows one connection and resident set size is huge, 8 gigabytes. Uh, Problem is that this mapping is distorted due to mapping of shared buffers. And for understanding it, we must go into so-called smaps kernel interface. And here is the output of a simple script which scrapes data from that smaps interface and pivots them. And for our purposes, that fifth line, def0 deleted, is most important because here are all those huge numbers. And this is the way how shared buffers are being mapped into physical connection. When we look at those other numbers, resident set size and mainly proportional set size, we see actually very, very small numbers. So when we now do this magic for typical situation when we have many connections with resident set size in summary exceeding physical memory on the machine, and we go into smaps interface and actually remove that def0 deleted line from our calculations, we now finally see what is the real memory usage of those connections. And there are some differences, and I will explain why. Because this is connected with the mystery of Workman. We all know Workman, but to actually show how it works, we need some scripts which will repeatedly scrape smaps for connection during query run and plot results. Here is great how it looks like. But don't worry, only that second and third graph in this whole mess is actually important because they show anonymous and heap memory. So if we run very simple query with default settings of workmem 4 megabytes and that dataset fits nicely into workmem, we can see this in our measurements. Very short, quick burst of memory usage, and that's it. When we plot it and scale it better, we can be surprised that actually workman was used 2 times in this very simple processing. Not one time, as it is usually discussed in different articles, but 2 times, which is not bad. Postgres used as much memory as it needed, but it also means that calculation based on one workmem are not exactly safe when we want to understand memory usage. So let's try this thing with a data set which does not fit into that workmem. And here we see different characteristic. But what is really important is that heap memory staying high at the end of processing. When I plot it, summarize it, Workman was used even more, 2.2 times. But that heap memory stayed somewhere around 1.5 Workman, which is something we would not expect. Problem is with the mechanism of heap allocation. At the end of that query processing, connection created some small objects on the top of heap, and that object will stay there until next query. Uh, Postgres actually deallocated memory which is below that small object, but since it is heap, it can only grow up and go down from the top. Even though Postgres sees these deallocated memory chunks as free, Linux actually still has these pages marked as dirty resident set size pages for that process. And this is another problem. What can happen with these connections, especially with small workmem size. There are two other internal limits of Postgres. One of them is scaling of multi-version concurrency control snapshot. It was improved in Postgres 14, and throughput is now stable. That blue text is linked to article on Microsoft blog. It also shows this diagram how throughput is now better, but with too many connections, this is still significant bottleneck. And last but not least, there is a bottleneck for too many locked objects per session, which was significantly changed in Postgres 18. But in Postgres 17 and older, it allows only 16 objects per session being locked locally using fast path mechanism. And everything else above it required access to central shared lock table, causing huge spikes of lightweight locks. So using latest Postgres in this scope is definitely a good idea because we can actually set it according to our needs. And that's it. Here are a few pages summarizing what I already said, but I will not repeat it. And that's all what I wanted to share with you. I will be on Discord, so don't hesitate to ask me. Let's discuss this stuff. And thank you very much for your attention.